In this lecture, we'll continue to talk about the big topic fast Fourier transform. Specifically, in this particular chapter, we're talking about the theoretical development of FFT, fast Fourier transform, corresponding to the situation where the capital N represent the number of sample data point can be expressed in terms of the two integer number R1 times R2. In the previous chapter, we say the integer R1 is equal to 4. For this chapter, we also keep R1 equal to 4. However, in the previous chapter, we talk about the integer R2, the second integer R2 is equal to 4. In this chapter, we say R2 is equal to 2. And the reason we want to consider the different situations so that you can get a different feeling so that we can obtain the general formula later on. Okay, so in this lecture number 20, we will look at the situation where the sample of data point capital N is equal to the product of two integer R1 times R2. And specifically, we assume R1 equal to 4, R2 equal to 2, and therefore the capital N is equal to 8 data point. Now, because capital N is equal to 8 data point, basically it means the index n, small n, and the index small k each can have the value anywhere from 0, 1, 2 up to 7, which is basically equal to capital N minus 1. Like in this case, capital N is equal to 8, and that's why n minus 1 is equal to 7. However, the value of the small index n and the small index k can be given by equation 54 and equation 55. And by the way, equation 54 is very similar to the previous chapter, corresponding to R1 equal to 4 and R2 is also equal to 4. However, equation 55 in here is slightly different and is given as k equal to 2k1 plus k0. The reason equation 54 and 55 they have a different form is because in this chapter the value R1 equal to 4, the value of R2 is different from the value of R1. In any way, equation 54 and equation 55 involve with the index n0, n1, k0, and k1. And the value of those index are given as indicated in equation 56, 57, 58, and 59. So, take a look, for example, if you let the value of n0 and you let the value of n1 have a smallest value. Well, the smallest value for n0 is 0. The smallest value for n1 is 0. And corresponding to that, the value of n will be 0. On the other hand, if you let the index n1 to be equal to the largest value you can have, which is 1 in this case, if n1 is equal to 1. And if you let the index n0 equal to the largest value you can have, which is equal to 3 in this case, this one is equal to 3. In that case then, you can see very clearly the value of the small index n is equal to 7, as it should be. And the same thing is true for the small index k. If you let k0 and k1 both equal to 0, then the value of the small index k is equal to 0. On the other hand, if you let the index k1 equal to the largest value, which is 3, if k1 is equal to 3, and you let index k0 equal to the largest value, which is 1, this is equal to 1, then again the value of the small index k will be equal to 7. That's the largest one you can have. So the definition of the index n and k are given in equation 54 and 55, whereas the definition of n1, n0, k1, k0 is given by equation 56, 57, 58, and 59. So with that much of the definition, then if you remember earlier, we have a formula which say C tilde is a function of n is equal to summation on the index k of f depending on the index k multiplied with the function w raised to the power n k. This is a formula that we have it in earlier chapter when we talk about informal fast Fourier transform. Now in this particular case, because we express the index small n in terms of a pair of index n1, n0, and we express the small index k in terms of a pair of index k1, k0, and also we replace the value of small n by the formula that we talked to you earlier, which is n small n equal to 4n1 plus n0. And we also replace the small index k by the formula small k is equal to 2k1 plus k0, as I showed you on the previous slide. Then what we have is equation 60. So that equation 60 basically just like equal to the previous equation that I wrote in red color, and we just substitute the value of small n and small k in terms of n1, n0 and k1, k0. Nothing big deal. Now let us try to pay attention to the term w raised to that power is shown in equation 60. That term I show you here on the left side of equation 61. Now if you pay attention to that term, what we can say is, let's try to do some expansion on the power of w. For example, if you take the first parenthesis, you multiply with the first term of the second parenthesis, then you will get this power term right here is indicated in equation 61 in the red color. On the other hand, if you take the first parenthesis and then you multiply with the second term of the second parenthesis, as I show you on the by the green arrow, then what you have is the power term as I show you in the green color of equation 61. Now let us pay attention to the first term, which is w raised to the power 4n1 plus n0, the whole thing times 2k1. That term can be expand a little bit more. For example, if you take 4n1 times 2k1, then you will get the power of 8n1k1. Similarly, if you take the term n0 times 2k1, then you will get this term right here, which is 2n0 times k1. The reason we want to do that is because when you look at equation 61, what I'm trying to tell you is the term that you see in the square bracket, which is w raised to the power 8, that term I can prove to you very easily it should be equal to 1. The reason is because w by definition is equal to e the term w that you have in the green bracket, this term right here that you have in the square bracket. See, oh, the term that you have in the square bracket, you can see the term you have in the square bracket, which is w raised to the power 8, right? That term over there can be computed like this way. The definition of w is equal to e raised to the power minus I times 2 pi divided by capital N. That is w. And then we want to raise it to the power 8. So we want to raise it to the power 8, and therefore this term here you have to raise to the power 8. But in this particular case, the value of capital N is equal to R1 times R2, and R1 is equal to 4 times R2 is equal to 2, so capital N is also equal to 8. So for that reason, e raised to the power minus I 2 pi over capital N, the whole thing raised to the power 8, is the same thing as e raised to the power minus I times 2 pi, minus I times 2 pi. And if we make use of the so-called Euler identity, then that term is equal to 1. So for that reason, we say w raised to the power 8 is equal to 1, and therefore what we have left is just the simplified version of equation 61, because the right hand side of equation 61 just become this term, equal to that term right there in blue color, which I show you again in the equation below that. So now, with that much in mind, equation number 60, we can rewrite it in a different simplified form. Okay? Like for example, in equation 60, if you take a look at it, on the left hand side you have c tilde n1 comma n0. That term is here on the left hand side. On the right hand side you have summation on k0 go from 0 to 1. That term is here. And then you have also summation on k1 go from 0 to 3. That term is right here in equation 62. Then you have f of k1 comma k0. That term is here. And then finally the term w raised to the power over there is right here as shown in equation 62. So this is what you have. Now you can see very clearly